Hi statisticians, this is section 9.2. This section is going to be very similar to section 9.1. Our goal is the same. We are using hypothesis testing to basically test kind of a guess about the mean, the population mean, mu. Now, before we start, because like I said, it is going to be very similar to what we've already done, I do want to remind you of a little decision tree that we used in chapter 8. So, remember in chapter 8, when we were like finding confidence intervals and using, we were using the Z and T distribution, we asked ourselves the following question: do we know sigma? Do we know the population standard deviation? And if the answer was yes, we do know sigma, then we would use Z. And if the answer was no, we do not know sigma, in that case we would have S, but we would not have sigma, then we would use T, the student's T distribution. So that's pretty much exactly where we're picking up here in section 9.2. Now, the last time that we talked in section 9.1, we were using hypothesis testing to test the mean. In that case, we did know sigma, and we used Z. So today, we're on the other branch of this tree. So today we're not going to know sigma. We will know S, but we won't know sigma, and we're going to use the student's T distribution. So the first example is going to be a warm-up. So basically we're still going to be in the first case here. So this one's just a practice for something that we've already done. Okay, sunspots have been observed for many centuries. Some archaeologists think that sunspot activity may somehow be related to prolonged periods of drought in the southwestern U.S. Let X be a random variable representing the average number of sunspots observed in a 4-week period. A random sample of 40 such periods from Spanish colonial times gave the following data. Okay, so again, each of these data values represents the average number of sunspots observed in a 4-week period. So this is like the average number that we observed in 1 month. This is another average number that we observed in another month, and so on. The sample mean is X bar equals approximately 47. And we've got, let's see, previous studies of sunspot activity during this period indicate that the population standard deviation is 35. Now, let me just stop right there for just 1 second. Notice this is sample. This is a sample. Actually, it says it right there. This is a sample of data. So we've got 40 data values in our sample. They gave us the sample mean. If they hadn't given us any other information, so if they had not given us this population standard deviation, we could have used our calculator to find S. So we could have used our calculator to find the standard deviation for this sample data set. Now, in this case, what they actually did was gave us the population standard deviation, which we could not have just gotten from this sample set. Because remember, the population standard deviation represents the entire population of all of these sunspot data values, which we don't have. Okay, so they would have to give us this. It is thought that for thousands of years, the mean number of sunspots per 4-week period was about mu equals 41. Okay, so this is definitely an important value. Mu equals 41 is an important value. We would like to know whether the average sunspot activity during the Spanish colonial period was higher than the long-term average of mu equals 41. This is also an important word there because that tells us what kind of test we're going to be conducting. Okay, first things first, establish the null hypothesis and the alternate hypothesis. Okay, so remember the notation. We always start with an H and then subscript, like a little subscript 0. We call this H naught. and then a colon. So always starts the same way, and our alternate hypothesis is going to be H1 and then another colon. Now, the null hypothesis, H naught, is basically saying nothing has changed from this thing where it used to be. So the null hypothesis is going to be that mu is still 41. Our alternate hypothesis is going to basically use these same values, the mu and the 41, but it's either going to be greater than, or it's going to be less than, or it's just going to be not equal to. So we just have to figure out from the words of the problem which inequality symbol goes here. And that's where this word higher comes in. So we want to know if the average sunspot activity is higher, meaning that it's greater than 41. So here's our alternate hypothesis. Now, when we're establishing an alternate hypothesis, remember we classify these by saying it's either a left-tailed or right-tailed or two-tailed test. So in this case, because it's greater than, it's basically like if we were looking at a number line and here's 41, we're wanting to know if the mean is greater than 41, so somewhere over here. And since we're kind of looking on the right side of the 41 on the number line, we say that this is a right-tailed test. Right-tailed test that we're going to be doing. Okay, since our sample size is greater than or equal to 30 and we know sigma, should we use the z distribution or the student's t distribution for the sample test statistic? And so that goes back up to our little decision tree up here. If we know sigma, then we use z. Okay, so we're going to use the z distribution. We're going to use a z-score for our sample test statistic. And so now we're going to convert the sample mean, 47, to a z-score. So basically using this formula, we're going to plug in all these numbers. So x bar is 47 minus mu, the original population mean, that's 41, over sigma, well, sigma is 35, over the square root of n is the sample size, and then it gives it to you right here, but also remember back up in the problem, they said a random sample of 40 such periods. So n, our sample size, is 40. Okay, so we'll plug that into the calculator, round to 2 decimal places because this is a z-score. So round to 2 decimal places, and then we're going to go to our table after that. So I found a z-score of 1.08 in my calculator, and now when I go to the table, the z-table, which I don't think I have on here. So when I go to my z-table, the p-value that's associated with a z-score of 1.08 is 0.8599. However, remember that this represents the left area. That z-table always gives us the left area. And since this is a right-tailed test, because we want to find the probability that the mean is greater than 41, so right-tailed test, we need to edit this area and basically use this to find the right area under the curve. And so the way that we do that is just to subtract this 0.8599 from 1, and that gives us 0.1401. So this is our p-value. That is our p-value. And essentially what that tells us is that there is a 14% probability that the population mean really is 41, and that kind of like our data is consistent with that. There's a 14% chance that this data could still be from a population with a mean of 41. Now, that's a fairly low probability, and at this point we can't conclude the test because they haven't given us that value of alpha. Remember, the level of significance is called alpha. So just a note here, we don't have alpha, and that just tells us we can't reject or fail to reject our null hypothesis. Basically, we can't conclude our test at this point. All we can say is, well, there's a 14% chance that that data really is consistent with a mean of 41. Okay, so just to summarize what we're doing, when we know sigma and remember the population, or the sample size rather, has to be greater than or equal to 30, we state our null and alternate hypotheses, and we state the level of significance. This has to be given to us in the problem. We compute the z-score. So we start with our hypotheses, we change our sample test statistic over to a z-score. We use the z-score and the table to compute the p-value, which is just the area. The p-value and the area are the same thing. And if the p-value is less than or equal to alpha, we reject our null hypothesis. Otherwise, we don't reject our null hypothesis. Okay, so following up on the warm-up, if we have a level of significance of 0.05, in other words, 5%, should we reject H0, our null hypothesis? Now, remember the picture kind of looks like this. Wherever alpha is, so 0.05, if our p-value is over here, then this is okay. If our p-value is over on this side, then we reject our null hypothesis, H0. Now remember, our p-value from that problem was 0.14. Here's our p-value. And so we're still in the okay range. Even though 14% is a fairly low probability, it doesn't cross over this threshold where we would actually reject our null hypothesis. So should we reject H0, the null hypothesis? We fail to reject. We fail to reject H0. I know it's weird language, but it's sort of like a double negative here, but this is how we say it. We fail to reject H0. Okay, now the other situation is almost the exact same steps with one pretty critical difference. Testing the mean when we don't know sigma. You still have to have your sample size greater than or equal to 30. You'll still state the null and alternate hypotheses. You use the exact same notation. Instead of converting your sample test statistic, your X bar value, to a z-score, now we're going to convert it to a t-score. So we're going to use that student's t distribution to go forward from here. So we use the t-score and we use the type of test, so either one-tailed or two-tailed, to compute the p-value of this statistic. Now, I'll show you in just a second how to find the p-value using your student's t distribution table. Also, and then just highlight this if you would. If the t-score is negative, which happens occasionally, basically you just ignore the negative and just use a positive t-score. And so we conclude in the same way. If your p-value is less than that cutoff, then we reject H0. And otherwise you say we fail to reject H0. And I would just add one more little note in here, actually two notes. First of all, the formula for converting a X bar to a t-score is almost the same as the z formula, so X bar minus mu, except instead of sigma over the square root of n, now we're going to use S over the square root of n. And then one other thing, remember when you're using that T table, everything basically depends on the degrees of freedom, which is just your sample size minus 1. So 2 important things to note for any time that we're using the student's T distribution. Okay, so let's see this in action. The drug 6-MP is used to treat leukemia. The following data represent the remission times in weeks for a random sample of 21 patients using this particular drug. Okay, so these are basically a number of weeks. From this data, now honestly, this does not have to be given. From this data, we could use our calculator to get the sample mean and to get the sample standard deviation. So remember, if you want to do that, you enter this data into one of your lists, you do stat, you do calc, and then you would go to one variable statistics. And so that could give you X bar, your sample mean, and it can also give you S, your sample standard deviation. Remember, in your calculator, it looks like that. Point being, it's friendly if they give it to you in the problem, but they don't have to give it to you in the problem, and if they don't, you can just real easily find it using your calculator. In this case, we don't have to. The sample mean is given as 17.1 weeks, and the sample standard deviation is approximately 10. Okay, so let X be a random variable representing the remission time in weeks for all patients using this particular drug. Assume that X is mound-shaped and symmetric. I want to focus on this sentence really quick. So just pause for a second and think about why that sentence is necessary in this problem. Think about what about this data makes it necessary for us to know that it's basically already normally distributed. And so hopefully you've come up with something about that number. This is a pretty small sample. So remember, 30 is the cutoff. If we don't know that our sample is normal already, then we need for our sample size to be greater than 30, and this definitely is not greater than or equal to 30. Now, if you don't have a sample greater than or equal to 30, then you have to know that basically it's already normally distributed. It's important for us to know that. So it's good that they included this sentence in there. It's necessary for us to know that to continue the problem. Okay, a previously used drug treatment had a mean remission time of mu equals 12.5 weeks. So this is basically our starting place. The question for us is, do the data indicate that the mean remission time using the drug 6-MP is different either way from 12.5 weeks? And we're going to use a level of significance of 0.01 or 1%. Okay, so anytime we're using one of these hypothesis tests, we always start in the same way. We state our null and alternate hypotheses. We're going to use the same notation for these every single time. So H naught and then a colon, H sub 1 and then a colon. Our null hypothesis, remember, is basically that nothing has changed from the previous data. So our null hypothesis is that mu equals 12.5 weeks. And just in case you don't remember from the section 9.1 video, your null hypothesis is always going to have an equal sign. It's always going to be mu equals something. So this makes perfect sense that it looks like an equation. Now, your alternate hypothesis is going to be an inequality. So it's either going to have a greater than sign, a less than sign, or a not equal to sign. And to figure out which symbol, we need to kind of use the words in the problem. So in this particular problem, it says, is the remission time different either way from 12.5 weeks? Meaning we don't want to restrict to just greater than or just less than. We want to test both directions, and we just say not equal to 12.5 weeks. So now that we have that written down, we can classify this test. Because it's not greater than or less than, it's kind of both. We say this is a two-tailed test. We're testing both sides. This is a two-tailed test. Okay, so let's just compile what we know so far. We know that our sample mean is 17.1. Our sample standard deviation is 10.0. Our original population mean is 12.5. And our sample size is 21. This should kind of raise red flags, but remember, even though it's smaller than 30, that's actually okay in this case because they told us that our data was approximately normal to start with. So, following the same little decision tree that we talked about at the beginning of the section, do we know sigma? Well, the answer in this example is no. We don't know sigma. What we do have is the sample standard deviation, but we don't have the population standard deviation. So if you don't know sigma, you're not going to use z, you're going to use the student's t distribution. So that's how this section is just a little bit different than section 9.1, but other than that, the exact same process. So we're going to use t. And to use t, we'll take our x bar value and convert it over to a t-score using this formula. Now, just take a look at this formula really quick. So x bar minus mu over over s over the square root of n. And then let's think back to the one we used in the warm-up, which was almost the exact same formula with one pretty significant difference. Now, where we have an S, it used to be a sigma. But of course, it couldn't be sigma because we don't know sigma. Okay, so let's plug in these values. Everywhere I see the x bar, I've got a 17.1. Everywhere I see mu, I've got 12.5. Everywhere I see an S, 10.0 over the square root of n, which is 21. And so I'll just throw that into my calculator. Careful with parentheses, like make sure that your numerator is in parentheses, otherwise that'll throw things off. Same with the denominator. Square root 21. When I put this into my calculator, I put it in like this, just to make sure that everything kind of stays on the side of the fraction that I want. Now, the number that I'm getting here is 2.107988482. So I'm going to round to 3 decimal places. This is about 2.108. So there's my t-score. T is approximately 2.108. So now we've got that. Okay, so now that I've got my t-score, I need to find the p-value associated with the t-score, except there is another kind of significant difference here between t and z. We're not going to find one p-value. We're actually going to find a little bit of a range of p-values. So here's what I mean. In your formula sheet, here's what your student's t distribution looks like. So remember, everything here is based on the degrees of freedom. And the degrees of, whoops, that's not what I want to do. The degrees of freedom is just defined as the sample size minus 1. So in our case, because the sample size is 21, that tells us the degrees of freedom that I'm going to be focused on in the table is 20. So going back to my table, I'm going to look at, let's see, try to keep everything in one window. I'm going to look at this row only. So here is degrees of freedom 20. That means I'm focused only right here for now. Now remember, the t-score that we found was 2.108. So that's what I'm looking for in this row. And I notice, well, let's see, 1.497, too small, 1.725, too small, 2.086, also too small, and 2.528, too big. It's almost like my actual t value would go right between these two. It's somewhere between 2.086 and 2.528. I've got a too small on one side, and I've got a too big right here on the other side. Unfortunately, 2.108 isn't exactly in this table, and I'll just tell you right now, you're never going to find your exact t value in the table. Like, it just doesn't happen. Or I should say, it would only happen very, 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 very rarely. So you're always going to be looking for a too small, too big. Okay, so now that I've kind of focused on my too small, too big here, I've got my two different t-scores. I'm going to kind of walk these up to the top of the table, and you'll notice on the side, we haven't really talked about these two rows yet. We have the one tail area and then two tail area. Now, this goes back to the type of test. If you have a right-tailed or a left-tailed test, then you would use the one tail area, because right tail is just one tail, left tail, it's still just one tail. Now, if you're dealing with a two-tailed test, you're going to use this row, this entire row. And that's what we're doing in this problem. Remember, our test was two-tailed because it's a not equal to. So anytime it's not equal to, that's a two-tailed test. So I'm looking over here in this row, and I'm basically going to just take these two columns that I had already focused on and just walk those up. And so when I do that, I find a p-value of 0.050 and also 0.020. So these are the two p-values that I need. Now, on a z-table, we just found one p-value. On a t-table, you're always going to find two p-values, and we're going to sort of write it as like an inequality down here, or like an interval. So here's what I mean. From the table just now, we found that our p-value, is between, and I'll just read those off from the table again, 0.050 and 0.020. And if you see a problem with this, that's good. So just look at the order of those numbers. Which of these two numbers is bigger? This is like 2% and this is like 5%, right? So it's a little bit weird to write this kind of backwards order. It's like saying that a number is between, I don't know, 180 or something. I don't know. Some example. The bigger number is coming first. We don't really like for it to be in that order. So I'm going to change this around. Instead of saying the p-value is between 0.050 and 0.020, I'm going to rewrite this statement and just write it in the correct order. The p-value is between 0.020 and 0.050. So now that's in the correct order. So just to go back to this table, you'll notice that these p-values are increasing as we walk to the left. So like, for example, here's 20%, here's 25%, here's 50%. They're increasing this way. So you can sort of bypass that step that we just did if you just want to write the smaller number before the bigger number. You can just go right from here to that it's between 0.020 and 0.050. The point is, you just want to write these in increasing order. Write those numbers in increasing order. So again, our actual t value that was 2.108 is not in the table. That's pretty much never going to happen, that you're going to find your actual t value in the table. So what you're always going to do is find two. You'll kind of find a too small and a too big, and then you'll use that too small and too big p-value from the top of the table. So we just found that our probability, or our p-value, is somewhere between, let's see, 0.020 and 0.050. And I'll just make a note, just off to the side, you don't even have to write this down. The actual p-value, you'd have to get this from a computer. So we won't do this, but the actual p-value, just for your information, is about 0.048. So just FYI, that's the actual p-value, but we don't really have a way to get that. We have to just come up with like an estimate. So somewhere between 0.020 and 0.050. In other words, if you want to think of it as percentages, 2% and 5%. So now we have to decide whether we're going to reject or fail to reject our null hypothesis. So remember, our level of significance was 0.01, or 1%. So if I was making a number line, here's 0.01. If our p-value is over here, we would reject our null hypothesis, and if it's on the right side, we fail to reject our null hypothesis. And what we just found is that our p-value is somewhere between 0.020 and 0.050, so like this interval, which is still on the fail to reject side. So we do not reject H0. We do not reject our null hypothesis. So there's a couple of questions that you can ask here. One of the questions is, what would happen if this interval was sort of like straddling the level of significance? So what would happen if we got one p-value that was over here and one p-value that was over here? And I'll just set your mind at ease. We won't see examples like that. It will always be totally on one side or the other side. So you don't have to worry about like making a hard call there. All right, so let's do one more together. Archaeologists become excited when they find an anomaly in discovered artifacts. The anomaly may or may not indicate a new trading region or new methods of craftsmanship. Suppose the lengths of projectile points or arrowheads at a certain archaeological site have a mean length of mu equals 2.6 centimeters. A random sample of 61 recently discovered projectile points at an adjacent cliff dwelling gave the following lengths in centimeters. So here's all of our data. Also, 61 is a pretty sizable sample, definitely bigger than that 30 that we would be worried about, so we're all good there. Let x be a random variable that represents the lengths in centimeters of all projectile points found at the adjacent cliff dwelling site. First of all, notice the problem did not give you your sample mean. It also didn't give you your sample standard deviation, and it also didn't give you your population standard deviation. So we'll have to find this stuff. So enter the data into your calculator to find the sample mean and the sample standard deviation. So pause your video now, enter this into list 1, and then do stat, calc, and one variable statistics. So hopefully you've had a chance to put that list in your calculator. When I did, I got about 2.92 for the sample mean, and I got about 0.85 for the sample standard deviation. The question is, do the data indicate that the mean length of projectile points in the adjacent cliff dwelling is longer than 2.6 centimeters and use a 1% level of significance? State H0, our alternate hypothesis, and alpha, the level of significance. Okay, so our null hypothesis is basically that nothing changed from the population mean that was already given in the problem. So still this, mu equals 2.6 centimeters. Our alternate hypothesis is going to be mu is either greater than or less than or just not equal to 2.6. And so we have to get a clue from the problem which way they want this inequality to go. And the clue is right here, longer than 2.6, so greater than 2.6 centimeters. Use our 1% level of significance, so alpha equals 0.01. Okay, part B, what sampling distribution should you use for x bar? Should we use the standard normal, which just means z, or the student's t-distribution? Once you decide which one to use that distribution to find the value of the sample test statistic. When you read the phrase sample test statistic, it just means z or t. Okay, so let's think about it. Which one should we use on this problem? Well, really the question just comes back to, do we know sigma? Do we know sigma? If the answer is yes, then we use z, and if the answer is no, then we use t. And in this case, no, we don't know sigma. Well, we know s, but we don't know sigma. And so we're in this case, here's s, we're going to use the student's t distribution. So we'll use the formula t equals x bar minus mu over s over the square root of n, and we'll plug in the values that we have. So x bar was 2.92. Our population mean was given to us as 2.6. The sample standard deviation is 0.85, and the sample size is 61. So when we throw that into our calculators, and again, I would suggest that you put parentheses around the numerator and also parentheses around the denominator here, and we'll round to 3 decimal points. I get 2.940 rounded, 2.940. Okay, so there's our t. This is our t score. Use the student's t-distribution table from your notes or from your formula sheet to find an interval containing the p-value. Okay, there's one other thing that we need to know before we go to the table, and that is the degrees of freedom. And remember, degrees of freedom is just our sample size minus 1, so in this case 61 minus 1, so our degrees of freedom is 60. Okay, so going to our table, which I've really done a bit of a number on over here. Going to our table, I'm going to start by looking at the row for degrees of freedom 60. Okay, so going, oh no, I don't, hopefully I have the next page. Oh my gosh. No, I do. Oh, whew, crisis averted. Okay. So here's my degrees of freedom 60. So I'm going to focus only on this row, and then what did we just say? Our t-score was what, 2.940? 2.940, which as usual is not exactly in this row. So I'm going to look for basically the interval. I'm going to look for 2 of these t-scores that would contain this one. Okay, well, too small, too small, too small, too big. So here is my interval. Here's too small, here's too big. Here's my interval, these last 2. Okay, so once I have those last 2, really all that does for me is just tell me which columns to use. So now I'm going to walk up to the top of the table, all the way up to the top here, and I'm going to be looking at one of these 2 area rows. So one tail area is for a right-tailed or left-tailed test, and 2-tailed area is for not equal to. So again, I'll just write that on here. If you're using greater than or less than, then you use 1-tail area, and if you're using not equal to, then that's 2-tail area. So on our hypothesis, our alternate hypothesis, we're using greater than. So in this case, it's a right-tailed test. Right-tailed test. And so on my formula sheet, I'm going to be here in the one tail area row. And again, I'm in these last two columns, so these two are my p-values. So you can do this in a couple different ways. You can write them out in the order that they're shown right here, 0.005 and then 0.0005. Or you can kind of write them in the correct order, just without kind of using like an in-between step. So of these two numbers, this one is smaller, 0.0005 and then 0.005. So I'm going to write them in ascending order just to start with. So I'll say my p-value. Actually, I'm going to use slightly different notation one more time. I'm going to say this. My p-value is between, and then I'm going to put the smaller number over here and the bigger number over here. So when I put these two inequality symbols like this, it's kind of a less than and then a less than, we read this p-value is between something and something. So it was 0.0005 and 0.005. Now the question becomes, should we reject H naught, and why or why not? So I'm just going to kind of do some scratch work over here. Remember, our level of significance was 0.01. 0.01, and what we just found for our p-value, these have more zeros than 0.01, so we found that our p-value interval was over here, smaller than 0.01. So should we reject H naught? Yes, because we're less than that level of significance. Yes, we should reject H naught because our p-value is less than the level of significance. If your p-value is less than your level of significance, we reject your null hypothesis. You reject H naught. Okay, so this is the last section. This is the last thing we're doing. The next thing that we'll do, the next video that you'll get is going to be a review section. So we'll go over all of the past exams. So that'll be the next thing you see. But essentially, now that you're finished with Chapter 9, you're going to take Exam 5, and then we will regroup to study for the final.